Hello guys, and welcome back to my YouTube channel. And this is the number one channel for structural insight and a place where you learn, build, and innovate. So today I want to talk about the case structs. But before this, I want to say something, and this is about those who will be sitting for their module 3 exams. Module 3 exams, and this is all about the structures 3. Structures 3. So I'm happy for those who are watching this video. So thank you for that, and continue watching them because they will help you somewhere in your exam. So one of my subscriber requested me to do videos on influence line, but I'm sorry I won't be able to start this topic because the time is so limited. I will not be able to start it and finish it on time so that you can prepare for your exams. But passing exams is your choice, and failing exam is your choice. So you have so many topics that you have been taught by your trainers or by your lecturers, and some of these topics, they always come in structure 3. For example, we have three-moment theorem, or the Clapeyron theorem of three moments. So this question will always come in your exams, and this one is for beams, for continuous beams analysis. Continuous beams analysis, and it is always 20 marks. So this is topic number 1. Topic number 2, we have a moment distribution method. Moment distribution method, and for this we have continuous beams analysis, we have portal frames analysis, and we have simple frames analysis. So again, this one will always come with 20 marks. We have another topic which we call timber design. To BS 5268, and it always comes with 20 marks. We have another topic called steel design. To BS 5950, and this is again 20 marks. We have another topic called influence line. This is number 5. Influence line. So this is again 20 marks. We have another one called steel connection and timber connection. So this one, it can either come or it may not. Again, 20 marks. So for you as a student, it is not necessarily you know all of these topics. So you can specialize. Specialize, it means you can choose topics which you think are so friendly to you and they are very easy or somehow easy for you to understand and comprehend. For example, three-moment theorem, it will always come. It will always come in your exams. So you can work on this. Work on this. Again, moment distribution is a must. It will come. Again, this one carries 20 marks. Timber designed to BS5268, it will always come. And also steel designed to BS5950, it always comes in your exams. Sometimes influence line may not come, or even this steel connection may not come. So what you are supposed to do, as I have said, specialize on the topics that you think are so friendly and very easy to understand and comprehend. For example, three-moment, you can work on three-moment so that when you receive your paper, make sure you have scored 15 marks and above. So let's say three-moment, you have scored 15 marks and above. Moment distribution, again, you have scored 15 marks and above. Again, let's come to timber design. Again, 15 marks and above. And then steel design, 15 marks and above. So you are supposed to tackle 5 questions, each 20. So this is 100 marks. But because of time, let's work on 1, 2, 3, 4 questions. So if you have selected 4 questions and you have scored 15, 15, 15, 15, so let's get the total. So this is the 10, 15, 20, 1, 2, 3, 4. So you already have 60 marks out of 100. So this is a credit. So you will get 3 in your exams. After exams have been released, you will score 3. So specialize on this. Don't study all of these topics. Just specialize and you will pass your exam very well. So for those who may find it difficult in tackling three-moment question and moment distribution questions, be it continuous beams, portal frames, simple frames, and so on, even timber, you can take a photo of the question. Just take a photo of the question and send me this question to my email, which is odavig@gmail.com, and I will be able to help you tackle such a question. So you can even work with past paper so that you can know what exactly is being tested concerning these topics. So go to past papers and check on them. The question that you think you are unable to solve, take a picture of that question and send it to odavig@gmail.com. So let's now go to cased struts. What is a cased struts? So these are a steel column cased with solid concrete. So for example, let me draw it here. So this is what we call a steel inside a concrete column. So this is an example of a cased struts. So this is a section of a column. This is for steel and this is concrete. Like that. So what are the reasons for these cased struts? Number one is to protect the steel column from corrosion. As you can see, if this steel is inside this concrete, it means the rusting will not affect this steel. So number two, act as a fire protection. So as you can see the concrete will protect this steel from fire effects. And then you have the increased load carrying of steel column, increased load carrying capacity of steel column, That is number three. Number four, prevent the column from buckling. Again, it prevents this column from buckling. Increase aesthetic value of the work. Aesthetic means beauty. Disadvantages: number one, you have the increased dead load, which is GK for the element. So if you do these cased struts, it will increase the dead load, which is GK for the elements. Then number two, increased cost of construction due to labor and material. As you can see, you are using two materials. One is steel and concrete. So it means you have increased the materials. So the cost of construction will be high. Slow the progress of the work. That is self-explanatory. Reduction in space. So if you use only the steel without the cased with concrete, the space will be enough. But if you use the cased plus steel, so the case will occupy more space compared to the steel. Therefore, the reduction in space. Increased construction quality control problem. So that is all about reason and disadvantages of cased struts. So let's talk about the general requirements for cased struts. So requirements governing design of cased struts are set out in section 4.14 of BS 5950 part 1. So the requirements are as follows. Number 1, the steel section is to unpainted. So is to be unpainted and free from dirty, grease, nail scales, etc. So requirements number 2, the steel section is solidly encased in ordinary dense structural concrete of at least grade 25 to BS 8110. The surface and edges of the flange of the steel section have a cover of not less than 50 millimeter. So you will see this later in the drawing. So let's proceed to number 4. Number 4, we have the casing is reinforced using steel fabrics, compliance with BS 4483. Alternatively, steel reinforcement not less than 6 millimeter in diameter may be used in the form of a cage of longitudinal bars held by closed links at a minimum spacing of 200 millimeters. So you will see this later in the diagram. The reinforcement is so arranged as to pass through the center of the concrete cover. So the reinforcement is to pass through the concrete cover. The concrete extends the full length member and is thoroughly compacted. So the concrete extends the full length and is thoroughly compacted. Primarily, structural connection should be made to steel connection. So structural connection should be made to steel connection. Let's proceed to the next one. So number 8, the steel section is either a single rolled fabricated I or H section with equal flanges. So this is the diagram, and it is a diagram with I column inside this cased column. So as you can see, the flanges are of equal length. So this is the flange, and also this is the flange. Again, the minimum cover is 50 millimeter, and the maximum cover is 75 millimeter. So this is the distance for cover. This distance is for cover, and then we have the link closed link with 6 millimeter diameter at 200 millimeter center to center. And then of course we have the longitudinal bar. So these are the longitudinal bars. There are 4 in number. So 4 in number longitudinal bars, and the minimum is supposed to be 6 millimeter diameter. So again we have the distance DC. We also have distance BC. So BC, this distance from here to here, is given by D plus 100. 100 is a minimum cover, or D plus 150, which is the maximum cover. So this distance, as you can see, the cover is from here to here, and also from here to here is cover. So if you take 50 times 2, you'll get 100, then plus D. So D plus 100 millimeter, or the maximum cover is 75. 75 times 2 is 150. So 150 plus D, you'll get DC. The same apply to BC. So BC, you have this distance B plus 100 minimum, which is cover from here to here is 50, from here to here is 50. Or the maximum is 75, from here to here 75, from here to here 75, which is 150. So, and also this is the concrete. Inside we have a concrete of strength not less than 25 Newton per millimeter square. The last requirements, which say that the steel section is not to exceed 500 millimeter by 1000 millimeter deep. So it clearly say that this distance, it should not exceed 1000 millimeter deep, and this one should not exceed 500 millimeter. So that is all about the requirements. The allowable loads for concrete cast column is based on empirical loads given in BS5950. So number one, no, let's start with A. LE must not exceed the list of 40 BC, Roman 1, Roman 2, 100 BC squared over DC, and Roman 3, 200 RY, whereby BC is equal to minimum width of solid section, which is B plus 100. B plus 100. As you have seen in the diagram, DC is the minimum depth of solid section, which is D plus 100, and RY is the least radius of gyration of uncased steel section from the table of properties of section. Let's now go to B. So we are done with A. So we have number B. The radius of gyration should be taken as Roman 1. About x-axis should be taken as that of uncased steel section. So no formula for this. The one for uncased section will be the same as the one for cased section. About y-axis of the cased section, it should be taken as 0.2 BC, but never more than 0.2 into bracket B plus 150. Let's proceed to C. So we now proceed to C. The compression resistance, which is capital PC of the cased section, is determined from the following expression. So PC, which is the compression resistance, is equal to AG plus 0.45 FCU capital AC over PY, then into bracket PC, whereby capital PC is the compression resistance, AG is the cross-section area of the section, FCU is the characteristic strength of concrete, and it must not be less than 25 Newton per millimeter square. Then capital AC is the gross section, is the gross area of the closed section, which is BC times DC. Then small pc is the compressive strength of the cased section, determined using the radius of gyration about x-axis and y-axis. However, PC, which is the compression resistance, we have already seen that should not be greater than the short struts capacity, which is PCS of the section given by this formula. So PCS is equal to this formula. You have seen the AG is the cross-section area, FCU is the characteristics strength of the concrete, and it should not be less than 25 Newton per millimeter square, and the AC is the gross section area, which is BC times DC. PY is the strength of the steel. Yes, like that. So we now talk about when a cast column is subjected to axial load and bending. So when a cast column is subjected to axial load and bending, it must satisfy the following relationship. So number A, local capacity stroke section check. So this is the formula for local capacity. F over PCS plus MX over MCX plus MY over MCY must be less or equal to 1. And then B, overall buckling resistance check. So F over PC plus MX over MB plus MY over MCY, it should be less or equal to 1, whereby F is the applied factored axial load, and then PCS, short strut capacity, MX, applied moment about the major axis, and then MCX, the moment capacity about the major axis, which is given by PY times ZX. Then MY, applied moment about the minor axis. MCY is the moment capacity about the minor axis and is given by PY/ZY. And then PC is the compression resistance. MB is the buckling resistance, which is given by PBSX. SX is the plastic modulus. So we tackle one example. Cast column example number 1. Determine the compressive resistance of grade 43 steel 305 by 305 by 118 kilogram per meter universal column if it is cast in concrete of compressive strength 25 Newton per millimeter square. The column is 5 meters long and is fixed at both ends. So before I start tackling this question, allow me to write here the most important information to create so that I can rub here and create more space for our calculation. So the grade is equal to 43 and the size, the section size is 305 by 305 by 118 kilogram per meter. So the compressive strength FCU is equal to 25 Newton per millimeter square. And then the column is 5 meters long and is fixed at both ends. So this column is fixed at both ends and it is 5 meters long, like that. So solution. So the first thing to do is to go to the table of universal column and obtain the section properties of this size you have been given in the question. So determine the properties of the section or obtain properties of section of the section, which is 305 by 305 by 118 kilogram per meters. So I won't go to the table and show you how to obtain the properties because I have done it severally and I'm sure you know how to go to the table and obtain the properties. So the first properties is D. So D is equal to 314.5 millimeters. So allow me to write here allow me to write on this column, because I will rub here. So D is equal to 314.5 millimeters. Then you have B is equal to 306.8 millimeters. T, capital T, is equal to 18.7 millimeters. We have the radius of gyration about x axis 13.6 centimeters. We have the radius of gyration about y axis is equal to 7.77 centimeters. We have B over capital T is equal to 8.20. We have D over small t is equal to 20.6. And then we have ZYY is equal to 1760 centimeters cubic. We have ZXX is equal to 587 centimeters cubic. We have the plastic modulus is equal to 1950 centimeters cubic. And we have the area is equal to 150 centimeter square. ZYY. So let's cross check. So D is 314.5, that is correct. B is 306.8, that is correct. T is 18.7 millimeters, that is correct. RXX is 13.6 centimeters, correct. RYY is 7.77 centimeter, correct. B over T 8.20, correct. B over T 20.6, correct. ZYY 1760 centimeter cubic, correct. ZXX 587 centimeter cubic, correct. And then SX, which is plastic modulus, 1950 centimeter cubic, correct. And then the cross-section area is 150 centimeter square. So everything is okay. So if you don't know how to obtain this from this table, from the universal column table, you can visit one of my video for column design or beam design, and you will be able to see how you can read the table and obtain these values from the table. It is very simple. So let's now proceed to strength classification. Strength classification. So for strength classification, we always use T, capital T, which is the flange thickness, and the flange thickness is equal to 18.7 millimeters. So the BS5950, it provides a table which guides you on how to classify the strengths of a steel. So again, if you don't know how to classify the strengths of the steel, again, you can visit my videos, my video on the introduction on the design of steel to BS5950. But it's something which is very simple, so it should not worry you. So as you can see, 18.7 millimeters is more than 16. So 16 millimeter is less than 18.7 millimeters, and this 18.7 millimeters is less than 40 millimeters. So these are the guidelines provided in the table uh, the table of BS5950 on how to classify the strengths. So you will say, therefore, Py is equal to 265 Newton per millimeter square. So this is the strength of this section. And then we'll come and obtain a value for this, which is given by 275 over Py. So this one is equal to 275 over 265. So it's equal to 1.02, like that. After strength classification, we now proceed to section classification. So section classification. So for section classification, we will use the ratios. The first ratio to use is B, small b over capital T. So this will be for the flange. So this one is equal to 8.20. Again, BS5950, it provides a table that guides you on how to classify the section of a steel. So I'm not going to talk about that. So again, visit my introduction to design of steel to BS5950, or you can check one of my videos for beam design, and you will be able to see how this table can guide you on how to classify this section. So B over T is equal to 8.20, and it must be less than 9.0, like that. So whereby 8.20 is less than 9.0 times 1.02. So it is true, 8.20 is less than 9.0 times 1.02. It's not necessary you multiply this, but you can see it is true, 8.20 is less than this. Therefore, flange is class 1 plastic, like that. So we have now classified the flange. We now proceed to the web. So for the web, we will use a ratio of d small d over t, which is equal to 20.6. And from the table provided by BS5950, 20.6 is less than 80, like that. So this one is equal to 20.6 is less than 80, and this one is here 1.02. So it is again true, 20.6 is less than 80 times 1.02. Therefore, the web is class 1 plastic. As simple as that. And then we'll come and say the section, which is 305 by 305 by 118 kilogram per meter, is class 1 plastic. So section 305 by 305 by 118 kilogram per meter is class 1 plastic. And we are done with that. We now proceed to the slenderness ratio. Let's proceed to slenderness ratio. Before you proceed to slenderness ratio, let's calculate the LE, which is the effective length. So the effective length, LE, will be given by this formula 0.7 L, because it is fixed on both ends or at both ends. So LE is equal to 0.7 L. So 0.7 times L. L is 5 meters, so times 5. Convert this meters, 5 meters into millimeter, so times 1,000. So therefore, which imply LE is equal to 3,500 millimeters. So LE is 3,500 millimeters. You can come here and say LE is equal to 3,500 millimeters, like that. And then we come and calculate our distance BC. Distance BC. So BC will be given by this formula. Remember, if you have a cast steel like this, if this is a steel, a cast steel, like that. So if this is A, B, no, A, B, C, D, so this distance is what we call BC, and this distance is what we call DC. So to get BC, remember, it will be this is the cover, and this is the cover, and here, and this distance is what we call B. So to get BC, if you take the minimum cover to be 50 and also 50, so 50 plus 50 is 100. So it will be 100 plus B. So this one is 100. This one is B plus 100. We have already covered this. You can check in the in what we have just concluded. So it is B plus 100. The same case to this one. The same case to this. So if this is cover and also this is cover and this is D. So to get DC, it will be 50 plus 50, 50 plus 50, which is 100, which is 100 plus D. So that is for the DC. We'll come to that. So BC is equal to B plus 100, and we already have our B. So our B is 306.8. So this one is equal to 306.8 plus 100. So this one is equal to 406.8 millimeter, like that. And then we come to DC. So DC is equal to D plus 100. So this one is equal to, our D is already here, 314.5 plus 100. So this one will be 414.5 millimeter, like that. So we already have our BC and DC. Now let's now get the gross area, which is AC is equal to BC times DC. So this one is equal to 406.8 times 414.5. So this one is in millimeter square, because this is millimeter and this is millimeter. So if you multiply, you will get, so AC is equal to 168.6186 times 10 to power of 3 millimeter square. So you can come here and say BC is equal to 406.8 mm, and then BC is equal to 414.5 mm, and then you have this one, the AC is equal to 168.6186 times 10 to power of 3 millimeter square. Why am I writing this here? Because I will rub here and I will rub this information, and the information will help you in calculating various parameters. So we now proceed to this statement. The LE should not be greater than the least of the LE. The LE should not, the LE should not be greater than the least of, we begin with A. So this LE should not be greater than the least of, we begin with A. So A, we have 40 BC. 40 BC. So this is 40 times BC. BC is 406.8. So this one is equal to 16,272 millimeters. So this is the first case. The second case, or B, 100 BC square over DC. So this one is equal to 100 BC square is 406.8 square over DC. DC is here, 414.5. So this one is equal to 39,924.30 millimeter. So this is B. The third case, or C is 200 R, the RY. So RY is the radius of gyration about the y axis. So this one is equal to 200 times RY, which is 1760. 17, no, not 1760. It is 7.77. 7.77. So this is the radius of gyration about y axis, 7.77. Because it is in centimeter, you will multiply it by 10 to make it, to change it to millimeter. So this one is equal to 15,540 millimeter. So we have A, B, and C. So the statement says that the LE should not be greater than the list of. As you can see, 3500 millimeters, which is LE, or the effective length, is less than these three cases. So the first case is 16,272. The second one, 39,924.30. And the last one is 15,540 millimeter. So therefore, that 500 millimeters, which is LE, is the list of above values. Therefore, okay. After doing so, we now proceed to slenderness ratio. Slenderness ratio is symbolized by lambda. So for the cast section, Rx is the same as for the uncased section. So this is Rxx. Rxx is the same for the uncased section. So same as for the uncased. Section. And Rxx for the uncased section is here, 13.6 centimeters. So 13.6 centimeters. So the slenderness ratio for Rxx will be the slenderness ratio about XX will be, so slenderness ratio about XX is equal to LE over Rxx. So this one is equal to LE is 3500. Yes, it is here. 3500 all over Rxx, which is 13.6. You'll change it from centimeter to millimeter, so you'll multiply by 10. So this one is equal to 25.74, which is less than 180 for a dead and imposed load. So the slenderness ratio for about XX axis is okay. Now let's go to RYY. So RYY is the radius of gyration about YY axis. And this one is given by this formula 0.2 BC. So this one is given by 0.2 BC. So which imply RYY is equal to 0.2 times BC. This is 406.8 millimeter. So this one is equal to 81.36. And remember, there is a limit for r yy, the radius of gyration about yy axis. So it should be the limit is that 0.2 BC must not be greater than 0.2 into bracket b plus 150. So let's check. So we already have 0.2 BC, which is 81.36. Let's check if it is greater or not. 0.2 B, B, we have B as 306. So B is here, 306.8 plus 150. So let's check. So 0.2 into bracket 306.8 plus 150, it will give you 91.36. So 81.36 is not greater than 91.36. Therefore, okay. So you have to check for RYY. RYY, you have to check if it is greater than this or not. And it should not be greater than 0.2 into bracket B plus 150. So the slenderness ratio for y about y axis will be LE all over R YY. So this one is equal to 3500 all over RYY, which is 81.36. 81.36. So this one will give us 43.02, which is less than 180. Therefore, okay. So again, we'll come here and say the slenderness ratio for XX is equal to 25.74, this one, and for YY is equal to 43.02, this one, like that. Now we want now to proceed to what we call the compression strength, which is PC, small pc. Remember, we have the compressive resistance, which is capital PC, and the compressive strength, which is small pc. So the compressive strength, which is small pc. So we'll begin by PC about x-axis. So PC about x axis, and this one will use table 27B or 24B. Again, I won't talk much about this table because in the introduction to compression member design, I introduced you to this, or we talked about these two tables, which is table 27B and 24B. So just to remind you, we said that this table is for rolled steel section, and for you to use 27B, the T, it must be less than 40 millimeter. So to obtain PC about XX axis, when T is less than 40 millimeters, you'll use 27B or 24B. To obtain PC for YY axis, when T is less than 40, you'll use table 27C stroke 24 or 24C. So get the two difference, or visit the introduction to compression member design to BS5950. So let's proceed. Again, I assume you know how to read this table 27B or 24B, because in my previous examples, I have already shown you how to read these tables, and I'm not going to repeat. So we have this slenderness ratio, and here we have 200. This is Py, which is equal to 265 Newton per millimeter square. So for you to enter this table, you need these two values, the slenderness ratio about XX axis and the Py, which is 265. So Py is 265. So our slenderness ratio here for XX axis is 25.74. So if you go to this table, you will not get this value. This value is not available on the slenderness ratio column. So what you will do, you will go for a value which is slightly lower than this. For this case, it is 25. And it corresponds to 258 for Py. And then you will come to this one. This one will be at the center, 25.74 corresponding to X. And then we have 30. That is slightly higher than 25.74. It corresponds to 253, like that. Then after doing so, you will now do what we call the interpolation. And I've already shown you again how to interpolate. So it is not something new I'm introducing. So let's now do the interpolation. So before you do the interpolation, you'll get the difference between these two. So this is 0.74. This is 0.74. And again, this one, this is 5. Again, this one, 258 minus 253. This is 5 also. And here we are showing here is X. So you will do the comparison. 5 over 5 is equal to 0.74 all over X. To obtain X, we will cross multiply, which imply X is equal to, you will take 5 times 0.74 and then divided by 5. So which imply X is equal to 0.74, like that. So PC about XX axis is equal to 258 minus 0.74, which is equal to 257.26 Newton per millimeter square. We now proceed to PC about YY axis. So PC about YY axis. Like that. So again, you'll go to the table. So this one you'll use table 27C. Table 27C or 24C. Like that. Again, I'm not going to show you how to read this table. This is something you have done severally, and it should not be an issue for you to use it. So we have this, and we have 265. This is YY. So here we have 42 corresponding to 227, and then ours here is 40, 43, 43.02, 43.02 corresponding to X, and then 44 corresponding to 224. So you will get the difference. So here it will be 1.02, and then here this one is 44 minus 42, this is 2. Here we have 3, and then X. So just to do the comparison, 2 over 3 is equal to 1.02 all over X, which imply X is equal to, now take 1.02 times 3, cross multiply. 1.02 times 3 divided by 2. So you will get 1.53. You will get 1.53. So 1.53. So the PC about YY axis will be 227 minus 1.53, which will give us 225.47 Newton per millimeter square. And then the PC that we will use, it should be lesser between these two. So as you can compare, this is 257 and this is 225. So we'll not use this one because it is higher than this. So we'll use 225.47. So our PC will be 225.47 Newton per millimeter square. So let's now proceed to what we call the compression resistance check. So the compression resistance check. So PC, capital PC, is equal to AG plus 0.45 FCU AC all over PY multiplied by PC. So this one is equal to our AG, which is the cross-section area, is here. Cross-section area is here, 150, like that. Because it is in centimeter square, you convert it to millimeter square, so you multiply by 10 to power of 2, like that. Then plus 0.45 times FCU. FCU is here. FCU is here, 25, times AC. Our AC is somewhere. AC is here, which is 168.6186 times 10 to power of 3, all over PY, which is 265. And remember to multiply everything by PC, which is 22 to 25.47 to 25.47, like that. So our PC, our compression resistance, is equal to 49,934 Newton. So you will multiply by 10 to power of negative 3 to change it from Newton to kilonewton. So this one will be 49.98 kilonewton. After that, we proceed to what we call short struts capacity. Short struts capacity, because we said that the PC should be less than the short struts capacity. So let's check. So let me clean here. So you can come here and say PC is equal to 4998 kilonewton. So short struts capacity. So the short struts capacity is given by this formula. So this one is equal to, our cross-section area is here, 150, multiplied by 10 square. We are changing from centimeter square to millimeter square, plus 0.25. FCU is 25. FCU is here, times the gross area, which is 168.6186 times 10 to power of 3. Then our PY, which is 265. Then we'll multiply everything by PY, which is 265, like that. So if you carry out the operation, you will get 502.88 0.66 Newton. But since we want our answer in kilonewton, so you will multiply by 10 to the power of -3. So this one is equal to 528 kilonewton. So the question, you are told in the question to check to determine the compression resistance of grade 43. So the compression resistance is this one. This is the compression resistance, and it must be less than PCS. So we will conclude by saying that PC, which is 49.98 kilonewton, is less than PCS, which is 50.28 kilonewton. Therefore, okay, so our PC, our capital PC, is equal to 49.98 kilonewton, and the question ends there. So if you have not subscribed to this channel, subscribe and hit that notification bell so that you may be the first person to be notified when I upload a video. Like, comment, and share. So I end there for today, and we meet again in my next session. So thank you for your time.